Working with pairs of random variables. Let's look at this example from the book, page 162, Sum of the Draws. Calculate the distribution of x plus y for two random draws x and y from a box containing the set 1, 2, 3. In the first case, A without replacement and B with replacement. So we can visualize the joint distribution of x and y as points on a 3x3 grid. As seen in your book, if we're sampling without replacement, then we cannot get points on the diagonal of the grid. So in sampling without replacement, the joint distribution of x and y is only supported on these remaining 6 points. And it is uniformly distributed among these 6 points. If we're sampling with replacement, then we can get all 9 points on the grid. And so distribution of x and y in this case is uniform on these 9 points. On top of this picture, we can visualize the distribution of x plus y as drawn in your book. This makes it easy to compute the distribution of x plus y in each case. With this picture, we can also visualize conditional probability. For example, what is probability of x equals 2 given that x plus y equals 4 in each case? Given x plus y equals 4 simply means I'm restricting this diagram to this diagonal. So in sampling without replacement, probability of x equals 2 given x plus y equals 4 is 0. In sampling with replacement, then that probability is 1/3. Any conditional probability problems in Chapter 1 can be visualized with this technique. Now let's use this picture to visualize the difference between sampling with and without replacements for large N. Consider the same problem. I have x and y drawn from 1 to up to n, but now n is large. That is, if I'm sampling with replacement, then I'm sampling from this n square grid points. Whereas if I were to sample without replacement, then I'm sampling from n square minus n grid points. For large N, as we can see, the contribution from the diagonal is tiny. This is why, even though we sample without replacement from a large population, for example, in opinion polls, it is okay to approximate probabilities as if we're sampling with replacements. Here's an exercise. Draw two integers between 1 and n with replacement. What is the probability that the sum is less than n/2 when n is really large? For ease of visualization, let's normalize. So we work with x prime, which is x over n, and y prime, which is y over n. Then probability that x plus y less than n/2 is the same as probability of x over n plus y over n is less than a half, which is equal to probability that x prime plus y prime is less than a half. The point of the normalization is now x prime and y prime take values between 0 and 1 at increments 1 over n. We can visualize this as a grid with 1 over n overlaid on the unit square. X prime and y prime are independent and uniform, so the pair x prime y prime is a point chosen uniformly at random from this grid. Now, let's sketch the region x prime plus y prime less than a half. The probability x prime plus y prime less than a half is the probability that a point x prime y prime chosen uniformly at random from this grid lies below this line. When n is very large, the grid gets very dense. As n goes to infinity, x prime y prime is a point uniformly distributed on the unit square. So for very large n, we can approximate this probability x prime y prime lies in our region by probability that a continuous point uniformly distributed on the square lies in this region. This is equal to area of the region divided by area of the square. So the probability that x plus y is less than n/2 is approximately 1/8 for very large n. This is an example of a continuous approximation to a discrete problem. We already done this in Chapter 2, where we approximated the binomial with the normal. We will see other continuous distributions in Chapter 4.